Okay. But I was happy to see around 13 to 15 students at least have completed demo 3, right? That's very good, very good. Would have been nice if all had completed demo 3. Good. Let's continue the discussion, okay, on loop optimizations. The first one we'll talk about is loop invariant code motion. What is loop? What does the word invariant mean? Anyone? Huh? One that does not change. And what would loop invariant mean? One that does not change within a loop. Okay? If there is some expression which is computed inside a loop and there is a guarantee that its value remains invariant, then why are we computing it in the loop again and again? What can I do? Move it out. Compute it before, use it in the loop, right? What's the advantage? That expression is evaluated only once instead of many times in the loop. Okay, let's take a simple example to start with. I have a loop in which I am oh, this shouldn't have been there. It's a typo. None of you can see this line. None of you can see this line. You can only see till this point. Double invariant declared there. Okay. So the invariant is calculated here, right? What I can do is I can move the computation outside, right? I just want to prove a point there. All right. So what we are saying is we can move the invariant out, and this will save us a lot of time. We avoid computing. We avoid computing. Okay. Here is one more example. In that example, you said, hey, there are invariants, right? Let's look at one more example. What am I doing? I have a 3-dimensional array, 100 cross 100 cross 100. I am setting a sub ijk equal to I times j times k. Okay? How many multiplications am I doing? 2 million, right? 1 million, 2 million, right? 2 million multiplication. How many index operations I am doing? A sub, this is one index, one index, one index, and million times. 3 million array index operations. Okay. Can I do something about this code? What Jayashree is saying is this I times j is an invariant in the, but I've written for each, don't worry about for each, it's your for loop only. Okay. When I type the code, depends on my mood on that day, whether I write a for or a do. Okay. Yeah, so I times j is moved out. Let's do that. But what's the basis of doing it? How did Jayashree find that I times j is an invariant? In the k loop? Sorry, the k loop, can you repeat?
In the third loop, we are just multiplying the value of k and incrementing it.
Correct, but how did we know that I times j is invariant?
We are not changing the value of I.
We are not changing the value of I times j. How did we? See, as a human, you have extra powers. How will a machine check that? What analysis do you have to do? What can we do to say, hey, its value is not changing? Huh? Live, tell me, I mean, tell me what? I mean, just don't throw words. How will live range of what? So again, what is the question? Let's only focus on the innermost loop. Okay? And two superhumans or two people with superpowers have figured out that I times j is invariant. Right? It doesn't change. But how did I figure that out? See, if I am not a super person with a superpower, how will I know? I need to have series of steps using which I have to tell I times j is invariant. How? If I see the which for loop, the k loop, okay. The only variable which is changing is k, okay.
So we are multiplying that k, right? And I and j are the same value because they are not being incremented or anything in the innermost form.
So you are saying I and j's values are not changing. Instead of I times j, now we broke it down to i's value is not changing, j's value is not changing. Okay. No, this is I mean that there's only one expression here. So the common sub expression, that is loop invariant code motion.
Or otherwise, we can do one thing. Like we can unroll.
Some people also call it as commoning, but yeah.
We can unroll the loop, then we will be able to see
No, but we made one of us said a point. No, let's find out instead of what is not changing, can we find what is changing? So pakka k is changing. How did I figure out k is changing? Because there is a k equal to k plus 1 here, right? So k's value is changing. What else is changing? A sub ijk, that there is a array element being changed, k is being changed, right? Yes or no? I know, so I have two, if I keep the set of elements whose values are changing, the negation of that set will give me what is not changing. Okay? Now if I have a set of, in this loop, what is changing? Let's only talk about, for the time being, scalars, not array elements, just ijk. What is changing? K. So now I have an expression I times j. Does this expression use any variable from that set which is being modified, which contains the variables that get modified? No. So what I am saying, focus on one expression, any one expression, find out if the set of variables which are changing, are they used to compute this? If they are used to compute it, it is not loop invariant, it is changing. If it is not used in this expression, then it is, that's the idea we will follow. So we will identify, so what is to do loop invariant code motion, I need to identify the opportunity. Remember we talked yesterday about three things. For any optimization, safety, opportunity, profitability. So profitability, we'll assume, okay, this is mostly profitable when I move it out. Yesterday we saw some cases where it may not be profitable, but that's okay. Okay. So we will identify loops. It's not enough that we identify loops. In loops we have to identify the invariant code. Only then we can hoist it up. Correct? So I'll identify the variables which are defined in the loop. I'll call them, let's say that set is loop def. Okay? Then for each expression I will check if it is using a loop def, a variable from loop def. If so, it is also, I mean, it is not loop invariant. But here is something, right? I mean, you will say, what about, may I borrow a pen, please? Let us say I have a loop. I have x equal, let's say this is loop I, okay? X equal to I plus 1. I is changing, so x is loop invariant, I mean the I plus 1 is loop invariant or loop variant? Variant. What about y equal to x? How? So what does it mean? I first marked I as in my loop def. Then I will look at, hey, there is an x which is being computed here. Its RHS is in my loop def. So this is also going to loop def. Right? Okay. And hence y also becomes loop def. Okay. There is a minor catch here. When we say safety, let's say I have a loop like this for I equal to 1 to n. I have, or I'll do something, okay, 1 to n, ठीक है. I have z equal to y 1 to, yeah, 1 to n, z equal to 0 by 0. Okay. If I move it outside, what will happen? There is an exception before the loop even starts. It may so happen the loop doesn't even start because the value of n is, yeah, value of n is, let's say 0 or less than 1. So moving the code outside, we have to be careful because the loop may not even execute. Okay, the loop may not even execute. Here is one more. Let us say this is like this. If some condition z equal to 0 by 0. This is loop invariant, but this is executed only in some path. Should I move it outside? So there are things to ponder about. When you should, I mean, can you always move it out? We have to keep the safety in mind, right? Okay. So what we will do, we'll come back to our previous example and identify loop defs. In the outermost loop, I is defined, j is defined, k is defined, and the array A is also changing. Second loop, j, k, a, third loop, k and a. Okay?
Can't we actually move it outside? Let us say it is in one particular branch and we move it outside. Since that particular branch was to throw an exception, if we move it outside, it is throwing an exception like before entering the loop itself. So
Is it safe? Let us say here you have a piece of code. Okay. I'll rewrite the code. Bomb enemy territory. Okay. And this condition is if caught, self-destroy. You move the self-destroy outside.
I mean, if the computation isn't dependent on the loop.
It is not. The self-destroy is independent of it, just that there is a condition. The condition which is dependent.
Caught
If the condition is independent, I can also move the condition outside.
yeah, that
I can move the whole thing outside. That's also possible. right? But even that's a problem. Why? Let us say my loop is, I have a loop, bomb enemy, okay, if true, self destroy. It's always, I mean, there's no if true also. There's no if true. I have a loop, all right, but what I'm doing is bomb and self destroy, because it's a UAV, it has gone there, it doesn't have enough fuel to come back. I don't want the enemy to catch it and open it up and do whatever. So its job is to throw a bomb and then self destroy. If you move the self destroy outside, not good. So we have to be careful about the meaning, right? So one can say, hey, the self destroy depends on bombing. Maybe it may not be so. I'm just saying be careful. Okay. Alright. Here we identify that K and A are loop defined. So I times J is loop invariant. So what can I do? What transformation can I do? Let's see who can answer. What's your name? Green shirt? Huh? Kshitij. Aha. Kshitij. What can be my loop invariant here? And what should I do? Loop invariant is I times J. What can I transform this to? I can calculate in the J loop. I'll say, let's say T1 equal to I times J and use T1 here. Good? Any other invariant you can see? Anyone else? But value of I mean, if I write T2 equal to I and use T2, not changing anything. Yeah? Yeah, what about it? If I am doing A sub I j k, it is basically saying do first A sub I, then do sub j, then do sub k. So there are actually this thing, right? When I write A sub I j k equal to blah, this can be seen as T3 equal to A sub I, T2 equal to A sub j, and then T2 sub k equal to blah. Just stare it for a minute, right? I am basically saying get me A sub I. If it is a three-dimensional matrix, I am saying get me first the 2D matrix by the ith matrix, right? The ith plane, right? In the ith plane, get me the jth row. In the jth row, I want to write to the kth column, right? So this is getting me the ith plane, jth row, right to the kth column, correct? So now here I am writing to A sub I j k. Do you now see any further? This right can be seen like that. Do you see any further invariants here? A sub I j can go here, and so A sub I j can go here. So that's what I did. I did T2 equal to I times j. Oh, yeah, this should be T2, huh? This should be T2. Yeah, and then T1 is address of A sub I j. Do you see any further invariants? A of I can go upstairs, correct? So far what we have done, we have only done loop invariant code motion, correct? How many multiplications do we have now? हाँ सेम गिनती करो काउंट 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 we how many did we have at the beginning 2 million now how many million 10,000 100 so from 2 million we came down to 1 million 10,000 100 the number of multiplications have come down significantly. What about array index operations? Million, sorry, why did I say 100? There is no 100 here, no? It's only million and 10,000. So multiplications are only million 10,000. The index operations, a million, 10,000 and 100, right? Do you see something? We first did loop invariant code motion for this. We found a new loop. Here we found one more opportunity for loop invariant code motion. We moved further up. It can continue. Okay? Are you fine so far? Okay. Let's look at one more example. Look at this example. Discuss with your friend and see if there is any loop invariant. Talk to your neighbor if you want. Should be very quick. I'll tell you something funny. I see that some students are looking, discussing. I see that some students are looking this side and that side. I said, what's happening? Then I realized they are not actually distracted. They are looking at the two TVs. There are additional TVs which are. Please continue. Fine, three of you, friends time. Hey, friends time. What can go up? Can anything go up? X equal to a times b can go out. If why what is the loop def here? I is clearly loop def. What else? And a. Okay, capital A. Small a times b is loop invariant. Correct? Let's look at one more quick example. So this is straightforward. Here is one more. Can you look at this code and convince yourself that loop invariant code motion cannot be done here? What is loop defined here? I is loop defined, so is X. The RHS here is depending on itself. Okay. So I cannot move X plus 1, X equal to X plus 1 outside. Right? So the RHS, see, it's not the LHS that we care for, it's the RHS. See, in the previous case, the RHS A times B was loop invariant. X is changing. X is defined in the loop, but the RHS is not. So focus only on the RHS, not on the LHS. X is defined, rather X was defined but the RHS isn't. So this expression is loop invariant. A times B was loop invariant, and we could move along with X outside because X was not being, what's the right word? Yeah, because just keeping the temporary, I mean, x here makes no sense here. We'll just move it out, it's useful. So x plus I is loop variant, it's changing because I is changing and x is changing. X is changing, but RHS is not. Because the RHS is not changing, I can say x is now not changing. Okay. Here is a small variation of the code which you will appreciate. I'll write the same code here for int I equal to 0, I less than n, I plus plus, int x equal to a times b, y equal to x plus 1, a sub I equal to x plus I. Is this visible to, no, better? Okay, this is the code I am talking about, right? What is loop def here? I is clearly loop def. So in my loop def, I will initially keep I, x is assigned in the loop, I will keep x, I will keep y, I will keep a. Okay, whatever is defined, I will just dump it there. Then I will say, is there any expression which is loop invariant? Is there any expression which is loop invariant? A times b, this is loop invariant. So I say, hey, I can move it up along with x. So I can move this one up, I can take out x from here. Okay, now I will ask the question again, is there any instruction which is loop invariant? Y. So this is x plus 1 is loop invariant, not y. X plus 1 is loop invariant. Because x plus 1 is loop invariant and y is not defined anywhere else, I can move this one outside. Okay. I'll just give one more, I'll just make one more this thing. So I'm saying this can also go up, correct? Let us say I have z equal to z plus y. Okay? Or rather, let me do something else. Z equal to y plus 2 and z equal to z plus 1, ठीक है, some such thing, not a big deal, some z plus something, z plus something that is changing, I want something, z plus I, okay, z equal to z plus I, ठीक है. Now let's do the same thing again. So this one has been already marked as invariant. So this definition is not, I mean it's getting always the same value. This is also invariant. What about x plus I? Is it invariant or not? X plus I, variant. Why? Because I is in loop def. I is in, so y is taken out, but I is still in the loop def. So this is not loop invariant. What about z equal to y plus 2? What about y? Y is now loop invariant. Y plus 2 is invariant. So now I am saying this is loop invariant. So I can actually write something like T4 equal to y plus 2. What about z? Can I move z equal to y plus 2 outside? Why? Because there is one more definition here. But so z plus 1, z plus I, is this invariant? No. So this is not invariant. So how do we move things out? See, when here I said x plus 1 I am moving out, so y also I moved out. But here y plus 2 was invariant, but I couldn't move z equal to y plus 2 outside. Why? So there are some expressions which are loop invariant, some are not. How do I move the LHS? RHS movement we are fine. LHS का क्या करें? Think about it for a minute. Discuss with your friend. I'll show you something, a simple solution to this. There are many ways you can solve it. I'll give you one such solution. Anyone? Any group? You see the question I'm asking, right? I'm saying there is one place where I said, hey, I can move x equal to a times b outside because the RHS was loop invariant. But here RHS is loop invariant. I'm saying, hey, don't move z. हो क्या रहा है? Huh? Right, but y was also, I mean, you are saying, hey, there is something more here, right? So there is some, we are doing z equal to z plus I. This is I. My handwriting is bad. So what will you do? Correct. But, oh, is it? So Jayashree is suggesting, why don't we try this? She's suggesting if I do z equal to y plus 2 and write z equal to z plus I, what will happen? Meaning is changing, absolutely right. See, if I move the whole thing out, moving just the RHS out is not an issue. Just if I move T4 equal to y plus 2 and use T4 here, it is okay. But if I move the whole thing out, लोच्चा हो जाएगा. All right, let's say y is a constant, right? Let's say y is 10. Just for my sake, just take it as y is 10. So z equal to 12. Then you will do z equal to z plus I. I goes from 1 to 100. What is the value of z? 12 plus 1 plus 2 plus 3 plus 4 plus up to 100. Instead, what's the answer you wanted? Z plus last value of I pretty much. Moving below the loop is possible, but in this case you can move below the loop. It's also another form of loop invariant. But let's focus on moving upstairs. Okay, you are right, absolutely. Madam, do you have the chocolates of yesterday? Yes, it's an excellent point raised by our friend that you know that the z plus I, only the last value of I care for. So I forget your name. Arnav is suggesting make T4 equal to y plus 2 and write z equal to T4 plus the last value of I, which is n minus 1. Right? This is also loop invariant. We could have done that. We could have moved this out totally. But for the time, I'll give you a chocolate for an excellent point. But let's only focus on moving it upstairs. So let's not look at this. Okay. So now my question is, on what basis can I move this one up and not this one? Here is my simple way to think. There are other complicated ways in which you can solve. Here is one. I will write like this: T1 equal to A times B, X equal to T1. I am not changing I am not moving X. Okay. Then what is it? Y equal to X plus 1. Okay. And the rest of the code. Now I will see the following. There is T1 equal to A times B, X equal to T1. Okay. Now if you look at this X equal to T1, this is X, this X, the RHS is a single variable. This is just that single variable. Why don't I simply replace this X with T1? This is called as copy propagation. X and T1 are going to have the same value. I'll rather replace it with T1. Let me do that. T1 plus 1. Excellent point. So if I look at X equal to T1, now I see that X is not used anywhere. Isn't it? This this definition has no use. I can eliminate it. So my code became T1 equal to A times B, Y equal to T1 plus 1. X hai ki T1 hai, how does it matter? Right? Isn't it? So I can first move the RHS out, then push the copies down, and then say I don't need this definition because this is unused, okay, or redundant. This copy is unused. I will throw it away. Let's do the same thing for Y. Now I have Y equal to T1 plus 1. What will I do? T2 equal to T1 plus 1 and replace this with T2. And then I have Z equal to Y plus 2, is it? Okay. I'll make it as T2 plus 2. Correct? And then Z equal to Z plus I. Okay? Now let's do the same thing again. This Y equal to T2 is redundant, unused, I can eliminate it. Okay? Now I have Z equal to T2 plus 2. I'll again do the same steps. I'll move T3 equal to T2 plus 2 and then replace this with T3. Okay? Correct? Now this definition, where is this definition used? Here. What I'll do, I can replace this with T3. Then this can go. This definition has no other use. This is also unused. So my code becomes, there is a sub I something na? Kya tha wo? A sub I equal to X plus I na? Somewhere here there was A sub I equal to X became what? T1. T1 plus I and Z equal to T3 plus I. What we did, we did step by step. We first moved the invariant RHS upstairs, use the temporary to hold that value, use the temporary. In my code, push the temporary inside. Now if I find the definition is no use, then Tata. Right? So we told Tata bye bye to 3 definitions, 1, 2, 3, all of which were invariant. And the program semantics still remain the same. Check with your neighbors once quickly that, moving this upstairs in this way. Neighbors time. Once you no, I think this example we already done. Yeah, check with your neighbor that you are fine with this example. Neighbors, check. Your neighbor is understood. You asked him. Good job. How about you? Were you there yesterday? No, right? Try to follow. But you can still talk to your neighbors. I mean, they can explain you if something is missing. Yeah? Yeah. So my loop def initially has x. My loop def has, by the way, so question is, hey, this cannot apply example. Why can't I move x plus 1 outside? Okay. What is my loop def initially? What does the set have? In this, for this, what is there in my loop def? I, x and a. Correct? In my loop def, I had I, x and you want to change the example? Which one? You don't want you want declaration of x and y to be outside. Okay, let's do that. So you want a loop which looks like y equal to x plus 1, x equal to a plus b, then, okay, this is an interesting example, we'll spend some time. Okay, I have x equal to 80, y equal to x plus 1, x equal to a plus b. Okay. What do we do here? So what is being defined here? Y and x. Correct? In my loop def initially I'll have y and x. Correct? Then y equal to x plus 1. This is in my loop def, so I can't. X equal to a plus b. This is RHS. This is loop invariant. What will I do? I'll write T1 equal to a times b. Replace this with T1. Okay? Now, which definition is reaching here? Now, we call, if I write a equal to something on b, the left side is called a definition, right side is called a use. Here y is defined, x is used. Here x is defined. Which definition will reach this use? No? So for this use, pay attention, two definitions will reach. This guy and this guy. If a single definition is reaching, I can dunk the RHS. I mean, like we did, we pushed T1 inside. Here, this definition was, only this definition was reaching. So I put this T1 here. Here, two definitions are reaching, 1 and 2. I cannot put T1 here. That would be incorrect. So I will still do x equal to T1, but here it will remain y equal to x plus. Did you understand the point, or should I explain again? Okay. Let us say the code is some loop y equal to x plus 1. And below that I have x equal to a times b. Before the loop there is some value x equal to 80. Okay. Now let us do loop invariant code motion. Correct? What are my loop def? Which variables are defined in the loop? Y and x. Whatever is there in the left side of the assignment here. So y and x both are in my loop def. Now let me look at the RHS. Is this loop invariant x plus 1? No, why not? Because x is in my loop def. So this is not loop invariant. What about x equal to a times b? Is a times b loop invariant? is A times B loop invariant? My loop def has X and Y. Okay. When I look at the RHS, I will look at each variable and see if it is there in my loop def. If it is the case, this is loop variant. Now I am doing A times B. Is A times B loop variant or invariant? Invariant, does not change. So I'll say, okay, good, T1 equal to A times B and use T1. So now I have X equal to T1. Now the question our friend raised, can I push this T1 here? This is X equal to T1, right? Now the code looks like X equal to T1. Can I replace this occurrence of X with T1? The answer is no, because this X, there is no guarantee that this X will get only this value. It can get either T1 or AT. If there is a guarantee, let's say there is Z equal to X here, then I can throw away this X and put T1, because at this X, the only definition reaching is this one. There are two definitions of X, at L1 and at L2. For this X, which definition reaches, L1 definition or L2? L2, single definition. Since it's a single definition, I can replace this X with T1. But here, how many definitions are reaching? Two of them, L1 or L2. Since I don't know which one can reach, I don't want to make a mistake by copying one of them, right?
Sir, at what point extending the liveness of T3, I mean in the above code,
Ah.
extending the liveness of T3 will affect inversely to what will do?
Loop invariant code motion can impact live ranges. My live ranges are getting extended, yes. So yesterday we had an example, all right? Yeah. Okay. So the point is, we can move a definition. I mean, we can get rid of some definitions also. Okay. But we have to be careful. All right. Let's get back to our loop. Any further optimization I can do here? There is no more loop invariants, right? There are no more loop invariants. Okay? Let me do some cheating then. Okay? Pay attention what I am doing here. Oh wait, this should be T2. Huh? I don't like it. I just change it to T2. Otherwise I keep looking at it and feeling bad about it. Ta na na ta na 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 na. Okay, good. Ready? Ani? All right. So this is T2 times K. Where is it? Yeah. This. Yeah, we were here. We were here. Look at this T2 times K. Just look at two things, the for loop and T2 times K, nothing else. What do you get? Huh? No, I am saying look at just the for loop and the expression T2 times K, nothing else. What need not be nested? K is loop, I mean K is changing. Alright, let's see. Is the value of T2 changing in the loop? No. Is the value of K changing in the loop? Can we make it to addition? How? Can we do some strength reduction? What do we want to do? First time iteration I equal to 1. What's the value of this expression? T2. Second iteration? T2 plus T2. Third iteration plus T2. Fourth iteration plus T2. Hey, this is cheating. You said multiply, but I am saying plus. No, not yet. Not yet. Not yet. Let's just focus on this expression. This expression says, yes, I am doing multiply with K, but essentially what I am doing is plus T2 with the previous value. Pay attention, plus T2 with previous value. Plus T2 with previous value. Why don't I compute the previous value? Store it before the loop. Just before the loop, let us say I say T4 equal to 0. I'll say T4 equal to 0, or K, maybe T4 equal to T2, sorry. T4 equal to the initial value. T4 equal to T2, and here I'll do T sub K equal to T4. And then increment T4 by T2. Let me just write it, you will be able to appreciate it. What I just focus on the last K loop. This is the K loop. I am saying I'll write T4 equal to T2, T1 sub K equal to T4, T4 equal to T4 plus T2. First time I am getting T2s, second time T4, T2 plus T2, third time T2 plus T2 plus T2. Sorry? How?
We can start the loop from 2.
Hmm.
And before that loop we can get T1 of 1 equal to T2. So that the first index is set. And in the loop we can do T1 of K equal to T1 of K plus
K minus 1. But that will add index memory operations here, index operations. I don't want to add that either. Because the two key things were memory and array multiply. Okay, we don't want to increase them. So what our friend was saying, why don't I do T1 sub K equal to T1 sub K minus 1 plus T2. But we don't want to increase the array operations either. Okay. Do you see what this loop is same as this loop? Everyone? Now pay attention, in the original loop how many multiplications were there? 1 million plus something. Now that 1 million is poof. 1 million multiplications are gone. All by doing what Jayashree said of strength reduction. Okay? So now is there a method to the madness? Yes, there is. We will spend some time on that. But let's look at few more such examples of strength reduction. Let's say I have code A sub I equal to B sub I times 4. That I can simply do with BI left shift 2. This is simple strength reduction. This is very simple strength reduction. Now if I have something like Ci equal to Di times I, but yeah, I could have also done A sub I equal to B sub I plus B sub I plus B sub I plus B sub I. That's also possible. Let's say instead of D sub I, let us say this is some Z times I. We could have again done what we just did. This Z sub I value we can replace with, Z times I can do it with continuous addition. Okay. Here is one more. I think this is very similar to what we did now. This is very similar to what we did. X equal to I times pi, y equal to I square. Okay. And there will be some uses of x and y. Don't say, hey, this is redundant, throw it away fully. Let's say there is some use of x and y. So what I can do, I can initialize pi times I equal to 0, the initial value. Similarly, I squared, I will keep it as initial value. Okay. Then x equal to pi times I equal to increment by this value. Can someone tell why am I initializing here with 0, but here I initialize with T2? Absolutely. Here I starts with 0. In that loop, K was starting with 1. So the initial value that I was writing here is 0. There rather pi times 0. Here I was starting with T2 times 1. The initial value we want to copy. Just like you said, no, copy the initial value outside. The initial value here is T2 times 1. Here the initial value is pi times 0. Correct? So that's what it is. This I times I, what can we do about it? This is a very cool this thing. So if I have, so what's the relation between a square and square of a minus 1? If I have a minus 1 whole square, I want now a square. What can I do? No, I am saying if I have some value a, I know it's a value of a square. If I know a square, how will I get a plus 1 whole square? I know a square. How do I get a plus 1 whole square? Let's call this as x. Then a plus 1 whole square equal to x plus 2a plus 1. Right? So I am using the old value. I am using the old value, then 2a plus 1. But this is a multiplication. What am I gaining then? This multiplication can be replaced with no multiplication. Right? Look at this way. I initialize I squared equal to 0. First time I will get 0. Second time I am saying I squared equal to I times 2 plus 1. Right? And then you can do one more round of strength reduction by doing this as I left shift 2. We hate multiplications, it looks. Just check with your friend that you are able to appreciate both the strength reductions. Then we will see a procedure to do it. Please check with your friends. Are you able to follow what we are doing? There's not much continuation from yesterday, but still, yeah. Yes, boss. Both. Has your friend understood? Hey, there is one more girl, Rana. She's missing today. Okay. Yeah. It should be. Sorry. Hey, this 2A is left shift of 1, not 2. Thank you. I don't know. I must be sleeping. At least. What's your name again? At least Nikhil is not sleeping. Okay. So there are two strength reductions we are doing. One for X, one for I, and both are different. Okay. But not always I can do this. Huh? Let us say I have A sub I equal to something times 7. Again, I this if I don't know the value of index, I cannot reuse the old value because I don't know what the old value can be. Just giving an example. There are some common reductions. This is not part of loop optimizations, but common things. In loop optimizations, we'll do this. I times k, we'll try to do it as I plus equal to k. I times 2, standard I left shift by 1. X by k, this is interesting. X by k equal to x times 1 by k. If there is an easy way to compute 1 by k, let us say k is a constant, say 2. X divided by some number, let's say 10. Let's say it is x is k is 10, let's say. Instead of dividing something by 10, multiplying with 0.1 is cheaper. So multiplication sometimes is cheaper. Yeah, there are times when you can use mask operations and operations. We'll skip that. Let's get back to loops because I feel I'll get sucked into it. Okay. So here is the way in which we will do. See, let us say my loop induction variable is I0 and it changes from I0, I0 plus 1, I0 plus 2 and so on. What is loop induction variable? This k here is the induction variable for this loop. Okay. Now, let us say in the loop, I have an expression that is of the form IC1 plus C2. I is the induction variable, C1 and C2 are constants. What does it mean? The values they will get are, first is I0 C1 plus C2. Second is I0 plus 1 times C1 plus C2. I0 plus 2 times C1 plus C2. So if I have an induction expression in my loop, if I have an induction expression in the loop, I can do something. What will I do? I will say, hey, I know the initial value. The initial value is I0 C1 plus C2. Outside the loop, I will insert code like this, t equal to I0 C1 plus C2. Okay. Wherever this expression IC1 plus C2 is there, replace it with this t. And then at the bottom of the loop, insert t equal to t plus C1 or C2? Why not C2? I'm not incrementing by, it doesn't increase by C2. The difference between this term and this term is C1. What I'm doing? 3 steps. for the inductive expression, for the induction expression, I am replacing it with a temporary. The temporary has an initial value which is the initial value of the induction expression, and the temporary t has to be incremented at the end. It should be incremented by what value? By C1, the value by which it changes. Okay. So use the initial value to set t and increase t by C1, right? All right. That's what we will do then. We'll replace this t times k. We'll replace this t times k with just one t5, some temporary t5, where the initial value of t5 is t2 times initial value k0, which is 1. Okay, and then I'll increment t5 by t2. There is one more here, t2 equal to I times j. This I times j can also be in the same form. So I will write some t4 equal to I and t4 equal to t4 plus I. Now I have 0 multiplications. I started with how many multiplications? 2 million. Okay. My index operations have come down, but they are still there. Can we do anything about them? Pay attention to T1 sub k. Just focus, like before, just focus on T1 sub k and the loop. To which location am I writing? Into which location am I writing? First time I will write to T1 sub 1. Next time, the next location in the array. Iteration 2, next location in the array. So if you look at the array that T1 is pointing to, first time I am writing here, which is star T1. Okay, this is star T1. Next time, if all I have to do is T1 plus plus, then I can continue to write to star T1. Pay attention to what I said. Let's say T1 is pointing to the beginning of the array, and I tell you I will only write to star T1. First time I will write to star T1 and then increment T1 by 1. So that for next iteration, T1 is pointing to the next right location. So that's what I will do. I would like to do here. So if this is my code. Okay, I will first expand. See, this is what I am actually writing to. Star T1 plus k minus 1. This is what I am writing. Right? This array is nothing but this. Correct? Similarly, this array is nothing but, when I say T3 sub j, this is nothing but T3 plus, remember it's a 3-dimensional array. It's a 3-dimensional array. When I go from one element here, the innermost, I am only incrementing by 1. But here I increment by one plane, right? So the 100 times j minus 100. Here, in the 3D space, I go from one plane to the other plane. So 100,000 times, 10,000 times I minus 10,000. So I have exposed the arrays, and then what will I do? So in this, it depends. In this language, I guess when I was in this language, let's say I start from the 0th index. Let us say T1 sub 1 is, in iteration 1, when I write to T1 sub 1, let's say it's writing to the first element, not 0. In C, the first element is 0, index 0. In C, when you write sub 1, it is numbered second element. But let's say there is a language in which it becomes the first element. Ah,
Shouldn't it be 100 times I plus j because you iterated over I, now you just
no, no, no. The 100 the I say how many planes have you crossed? In the plane, how many rows have you crossed? So this is giving me how many rows you have crossed. I number of planes, j number of rows, kth element in that row. So I want the jth row. Jth row. Each row has 100 elements. Let's no, it's simple. No? Let's say it's a 100 cross 100 cross 100 array. It means in 3D structure I have a single 100 cross 100 cross 100 cube. If I see it in 2D, it has 100 planes. In each plane I have 100 cross 100 elements. This says how many planes I have? 100 planes. In that plane, which row do you want? Jth row. Jth row. In each row, how many elements I have? In each row. So j times 100. In that row, you want kth element. This -1, -100, this thing is because of your indexing. If you switch your indexing properly, I mean, if you change your indexing, it can change. Okay? So now, look at this, I am writing to T1 plus K minus 1. Yeah, question? Correct. This is just exposing. This is not making any optimization yet. This is just saying, look, this T1 sub K is nothing but star T1 plus some offset. This T1 sub J is this and this. We are just exposing it. In the next step, I mean, if you look at it from this step, that's the same code as this. From this step, what I can do, hey, I'm doing here I'm going to the first element. So I'll do something like this. I'll have a temporary T8 equal to T1. T8 equal to T1 and then just write star T8 equal to this. And then increment T8 by how much? 1. Similarly, here I have T3 equal to, here T1 equal to T3 plus something, correct? This one also I'll replace with a temporary T7, T7 equal to T3 and increment T7 by 100. And same thing here, for this A plus blah I'll set T6 equal to A and increment T6 by 100,000, 10,000. See, the interesting part is, once I have code in this form, I am saying, hey, this K is increasing by 1, 1, 1, 1, 1. So this address is only shifting by 1, 1, 1, 1, 1. So I just increase by 1. Here I see, wait, this T1 increases by 100, 100, 100, 100. So I will add 100 to this. Here I say, hey, this is increasing by 10,000. So I will increase by 10,000. We can do further copy propagation and improve it further. कहीं लिखा तो होगा. See, there are a lot of unnecessary copies which can be simplified. But वो बाद में. Remember, we started with 2 million multiplications. How many multiplications? 0. We started with 3 million index operations. How many index operations? Gone, गायब, चले गए. Right? Poach. Isn't it beautiful? The compiler, which didn't know anything about our program, changed the hell out of the program. If we look at this program, we will say, oh, this is not my program. Right? But do you see that this can be way more faster? Because I'm not doing multiplication. As you know, multiplications are more expensive. Similarly, array index operations are quite more expensive than, this is just plain load. I'll tell you something more interesting. The star T8 equal to T5 and T8 plus 1. Just look at these two blue instructions. Stare at it for some time. Do you see something? Does something strike you? I am only saying just focus in this loop, the middle, the blue ones in the middle. T8 equal to T5 and T8 equal to, star T8 equal to T5 and increment T8 by 1. Huh? No, not quite. Do you know many architectures like say Intel architectures have this thing like load and increment, store and increment, right? Store. So I am incrementing the, so I can do star T8 plus plus. I can do star T8 plus plus. So what will do is, this is a single instruction. So the base pointer increments by with the same instruction. There are efficient ways in which you write to it and increment the base pointer. So this instruction pretty much will go away. Anyways, the point I am trying to say is that if we are careful to find opportunities in the program, right? There can be some amazing scenarios like this. Yeah. What's the time? Huh? 10:20. Okay. Fine. We will continue with our loop optimizations. Here is a code. I equal to 0, I less than 100. If flag, do something else, do something else. Okay. Look at this code. Tell me if this code bothers you. If this code is not making you feel uncomfortable, it's not good. It should make you uncomfortable. Or it should generate some feelings. Some may feel comfortable and say, hey, I can improve it. Some may feel uncomfortable saying that, hey, this is bad code. Yeah? Anyone? Flag is loop invariant. Good. Excellent. Either the if path will be taken or only one of them will be taken. Very good. Next.
Whole loop, that single part will only be performed.
In the whole loop, either I will be in the then part or in the else part. So, huh? Okay. So we will know. So we will know before the loop starts whether we will take the then part or the else part. Okay. So why? We see, we know that whether I'll take the then branch or the else branch, only one of them. Why should I move the for loop inside? Am I removing the if condition? But I don't know the value of flag. Absolutely. If you look at this loop, how many times I am checking the branch? 100 times. Pay attention, how many times I am checking the branch condition? 100 times. Okay? Fine. Now, if I transform it to this way, if flag, for inside, क्या होगा? Now this is, how many branches are there? Statically one branch. In the program, there is a single if. The code size probably has increased because of I pushed the for loop inside. But in terms of execution, at runtime, how many branches will I check in the generated code? Only one. Here, see, the branches are bad because they stop me from forming lot of transformations. Now, this whole code is inside this condition. There is no jump in between. So I am happy. This is called as loop unswitching. Okay. But to be able to do that, this condition must be loop invariant. This condition must be invariant. Okay. Let me see. I think I have one more small example for this. Coffee break in another, what's the time now? 10:30 is it? Yeah, we'll start with the coffee break in a minute. I'm okay. I think yeah, it's a good time because if we start loop tiling, it will take more time. Okay, we'll start for tiling once we come back. Yeah, so let's take a break. Have one group photo. So shall we have? Yes, said madam. So you'll do. Huh? Sorry? Huh? Yeah, I think it looks good. It's good. But wait. For we are always taking the photograph here only, no? In the same pose. Can we change? Can we change it to in some other way?
Yeah.
How do we change it?
I have two options.
Yes, 2/3.
One is that SRM is there,
Ah,
the tech park one.
ah.
There people like to have photographs. You can take there.
Oh, better go outside.
But you have to go down.
Ah. Any thoughts? Creative guys? Group photo can be a classroom photo. Okay, that's a good idea as well.